Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Welcome to this lecture. In this lecture, we will talk about an example about the related to the power generation plants. And in the power generation plants, basically they are very complex. They are very complex industrial systems. The power generation plants, and each component and there are so many components. For example, they have generators, the big components. They have turbines, and they have lot of bearings. um, Out of them, each component is further broken into smaller units for monitoring. Turbine is considered as very what you can say the key asset. All are key, but this is very expensive, and this is considered as a key asset. And this helps turbine. Basically what turbine does, turbine helps to convert various forms of energy, like hydraulic or steam, wind. You might have heard about wind turbines, coal, gas turbines, or even nuclear. And they convert all of this into very useful energy that is like, as a human we use it a lot: electrical engineering, electrical energy. Okay, so these turbines are treated as key assets. So what we need is, they also come up with a wide variety of very large number of sensors. The turbines, they have very large number of sensors, and each sensor is giving us different information. For example, the temperature of the bearings, the coil temperature, even the oil temperature, metal temperatures, and vibrations, harmonics, active power generation, reactive power, and so many things. So as a result, what we have is, we have a rich stream. We have rich stream of data, and often in like a near real or near real time, from hundreds of sensors, hundreds of sensors. And what we need is, we need to make a platform. So what we need is, or basically it is, everything is ready to provide a powerful uh, condition monitoring and predictive maintenance sort of platform. Okay, so this is the one of the best examples for if we are looking for condition monitoring. Always think about starting with this. If you are able to do this, this is a very rich and challenging example, and profitable or valuable as well, plus valuable, because turbines are very expensive. Okay, so understanding their mechanism and making a IoT product for them, it's very crucial. So by continuously analyzing sensor data, installed in the critical components of the turbine. So what we do is we have turbine and we have sensors installed with this, and sensors are going to give us data. Okay, so and what we do, we actually take the data, we do analysis, continuous analysis. So if we provide continuous analysis on the installed critical components, we can detect the benefit is we can detect early signs of failure, or even we can identify anomalies before any catastrophic equipment stoppage. So this is very critical, as failure in these rotating machines can lead to interruptions in the power generation of the entire cities. And IIoT actually plays a key role here, and it enables the remote. Benefit of IIoT is it enables remote condition monitoring. And this is monitoring, and it is useful in this case. It is useful in case of power generation, as it is mostly sort of distributed. For example, wind turbines or other places. So all data is stored, and we can save them as the data we have. The whole data can go to historian, okay, or the database, and due to the like limited computational capability, it is good to send it to a remote location for anomaly detection and the processing. It can go to, for example, even to the cloud for analysis. Okay, so there are so many options for this. Okay, so this diagram shows the architecture of the condition. This is showing like an architecture for the condition monitoring in power generation plants, starting from the turbines at the bottom. So we have turbines at the bottom. This overall is like an architecture for condition monitoring, right? And at the machine level, we have sensors which are collecting the data from the turbines, and then this data is sent as telemetry data in the real time, such as temperature, vibration, power levels. For example, this data is sent to the IIoT enabled DC system, which handles like control monitoring of the data, and then this data then flows upward through the multiple processing layers, and now at the ingestion layer, it collects and pre-processes raw sensor data, and then we have the data layer. This stores structured telemetry data that can be used for further for analysis, right? And then the analytics layer, it applies different kind of algorithms. This applies algorithms. It applies algorithms for anomaly detection, and fault diagnosis and performance prediction, prediction, and even the fault diagnostic. Okay, then we have a visualization layer, and this layers actually enables engineers. This enables engineers. This layer enables engineers to and operators to to view dashboards, and they know about the KPIs, how it is performing. Okay. Finally, we have the domain experts. They interpret these insights. Okay, so people at this level, they actually are the domain experts. And what they do is they interpret, the insights. Okay, to make, for example, maintenance decisions, and also they help us to optimize our operations. Okay, right. So this layer approach, this overall, you see the whole analysis is not done by a single way. This is like a layered approach. And this layer approach ensures that the data flows efficiently from your field devices to actionable items, insights. Okay, so basically this whole thing is helping us in two ways. Number one, it is helping us to predict in prediction. This is one thing. And the second thing that it helps is in prescriptive analysis for our power plant. Okay. Okay. So in this slide, we actually explore how different analytical techniques can be integrated to uncover the anomalies in rotating machines. So it is about and it is mainly to support the proactive maintenance. So the first step is about the statistical analysis, and this step is to provide, it provides an overview of the data by detecting the trends, the outliers, and missing values. It helps us quickly flag any unusual behavior. So this is quickly flags usual behavior. This is statistical analysis. The second step is about the unsupervised clustering. And unsupervised clustering, here we use the algorithms. Okay, and we try to find the natural groupings or clusters. Okay, algorithms to find natural grouping or clusters. Before it was called grouping. Nowadays, the common term is cluster. Okay, and this helps us to discover the patterns and associated variables with the machine assets. Then the third step is about the anomaly detection. Once we know the clusters, okay, what we can do is, the next thing is we can make like anomaly. We can apply anomaly detection techniques to find that significant deviates from the normal, indicating the faulty components, and the result is we are able to find the either the faulty component or some abnormal conditions. Okay, then comes the fourth step, which is about feature selection and predictive analytics. In this final step, this is one of the most critical steps. We focus on selecting the key features. So the key features are select key features, because till this point you have hundreds of features possible. Okay, so we have to find the key features that are most dominant key features, or the dominant features that influence or result in the anomalies, or able to detect the anomalies. Okay, then we detection I should write. Okay, and then we build the prediction models to anticipate the faults, and so finally we have the predict model. So combining all these steps gives us a very comprehensive framework for to monitor the machine health and prevent the unexpected failures. Okay, so this diagram is visualizing. It visualizes the end-to-end, a sort of end-to-end analytic process, which is used to detect the anomalies in the rotating machines like turbines. So the process follows from left to right, beginning with, like, the first thing is you do the statistical analysis. We first describe the data using the descriptive statistics and visualization tools, such as histograms and density plots. So this gives a baseline view. So this gives us baseline view. Okay. The second step is the unsupervised clustering analysis. Here we use the algorithms. For example, k-means clustering algorithm is well known to group the data points and identify the natural clusters, which helps detect the outliers or the deviations from the normal patterns. The third step is about anomaly detection analysis. At this stage, we apply the specific techniques. There are so many. For example, the outlier factor analysis to identify the data points that are likely anomalies. So, and they can be verified by the subject matter experts. Okay, we need subject experts. Subject experts. Okay, for either side. Then we have the predictive analysis, and finally we have the confirmed anomalies, which are used to train the here we train based on confirmed anomalies. Okay, so neural network is commonly used, or other machine learning techniques can also be applied to forecast the future fault conditions. So overall, this structured pipeline transforms the raw raw machine data into here actionable uh, insights for predictive maintenance. Okay. Okay. So the first step in the analytics process is the statistical analysis of the turbine data. This helps to the domain experts explore the data set at very basic level. Okay, so this is the explore the data set at very basic level. Okay, we understand, we look for the minima, maxima, standard deviation, averaging, and null values or missing values. Okay, so all of these. So we can have like a histogram. We can use histograms or density plots to visualize these, and these are very important. We try to make them and see. So statistical analysis also help us. So there is another very important thing that they help us to highlight the extremes. Okay, extreme outlier values, and this which could indicate like faulty readings or possible sensor malfunctions. Additionally, this step helps us to identify the any missing value or some other. Basically, this overall it helps us to get clean data. Okay, we have a raw data, and then we do this statistical analysis that help us to get the clean data, which is critical, and this is very critical. This is very critical stage before we go for using any advanced techniques. Okay, so if you apply any advanced techniques on this, chances are it will fail. But if you apply advanced techniques on clean data, the chances are, of course, the chances are good for that. Okay, so in this slide shows an example of a statistical analysis interface for the turbine data, and it's a little blur, but on the left side what we see is we see the statistics and the charts and advanced charts. This is the statistics, this is the data statistics, charts, then advanced charts, right? And in this main window, this is the BD. There is some sensor, one P air. Okay, the sensor and the histogram. Its histogram. This histogram. This histogram shows a normal distribution. And also the statistics indicate a very small variation across the 42 days. Yeah. And yeah, so and the next one, this one, Q and SOQ, these two sensors, they show a spread across the minimum. You see this one, it has a spread. Okay, it has a spread across minimum, maximum, and average value along with the standard deviation. So these are they are giving us a very interesting statistical summary, and that help us to these things help us to assess the sensor reliability. Okay, So this is looks reliable, but they have some issues. Okay, sometimes we have outliers and checking the data completeness before we move. Okay, this is important. Do always do this analysis, histogram analysis, always. Okay, before going further or using any machine learning or some sort of data science techniques, advanced techniques. Okay, advanced analytics. This is very important, right? 31 slide. Okay, so in this slide we focus on the challenge of identifying the abnormal behavior in the rotating machines. These systems generate a large amount of data due to frequency readings, and this data is we have a large amount of data, and this data comes from like multiple sensors, multitude of sensors, making it both like high. So what happens? Large amount of data, it has high frequency, and also it has like high dimensionality. High dimension. High dimension means multitude. Okay, it is multitude. Multiple sensors are giving us this. So traditional rule-based methods often they don't work here, and that's why unsupervised machine learning will help us. So in this case, unsupervised machine learning will help us. Okay, because of the high dimensionality and the frequency. So these algorithms actually what they do, they help to detect patterns and clusters. Okay, without needing labeled data. And this is especially useful because we often don't have prior examples of what is abnormal behavior. So by identifying the outliers in the sensor readings, using the clustering and distance-based methods, we can flag the potential issues early before they result in system failure. Now, this slide provides a very great view of how machine learning fits in the smart industrial environment, and especially for IIoT applications. So, starting from here, we see that the machine supervised learning. If you see the supervised learning and the unsupervised learning, this is how the machine learning is divided into two main branches. Okay, so in supervised learning, we already have labeled data and examples, for example, where we know if the machine is working normal or abnormal. And then we have the algorithms like decision tree, random forest, neural networks, SVM, support vector machines, and they are commonly used in the in IIoT for the fault classification and remaining life predictions. So they are used for fault and remaining life. Okay, so unsupervised learning is critical when we don't have the labeled data, and this is where the techniques we use clustering, k-means clustering or outlier detection, they become valuable for the abnormal uh, behaviors. Okay, abnormal behavior. So at the bottom left, we see the k-means clustering example here. And in the k-means clustering, before the k-means is applied, we don't have any idea about how to, what is the situation here, what is the no grouping or something. But when we apply the k-means clustering, now we can identify the three different groups. Okay, so three different groups are identified using k-means clustering. Right. So this helps us in IoT sort of applications to identify. Here we have a neural network model diagram. It shows that it has four inputs, four sensor inputs. Okay, x1, x2, x3, and x4, and they send the data to the hidden layer, and then we have a prediction output layer. Okay, this is predicting some value, and this is the foundation of many predictive analytic systems where the multiple sensors contribute to a final decision. So overall, in this slide, actually it connects uh, perfectly how the condition monitoring, anomaly detection, and how the condition monitoring and machine learning can help us to bring the maintenance, the condition based monitoring systems. Okay, right. So in this setup, we move further into the supervised technique. Okay, right. So in this step, we move further. We move deeper into the unsupervised learning techniques. So the goal here is to detect. So goal is to detect the outlier behavior in turbine sensor dataset. Okay, so the goal to achieve this goal, these could be the indicators of faulty sensors or unusual operation or even the potential failure of. So we use the k-means clustering here. K-means clustering algorithm it is a powerful technique for grouping similar data points. The benefit of k-means is it is powerful for grouping similar data points. K-means clustering, and it is based on the distance measure. Based on distance measure. Okay, so each observation is assigned to a cluster, helping us to visualize the groups of similar behavior in the sensor readings. So in IIoT system, this is extremely helpful because turbine data is high dimensional and continuous. So instead of labeling each data point manually, we allow clustering to show us the natural groupings, and more importantly, which points stand out as unusual. And since there are a lot of different designs, the turbines, okay, so there are so many different types and designs and types. So this you cannot have a one model for it. So the clustering method is the most suitable one to figure out what is the how they are being clustered together. And The next figure we will show you on the next page. We have a figure, and let's go there. Now you see we have these blue points, we have green, yellow, sort of green points and red points. Okay, so in this diagram, actually the blue clusters were highlighting the potential outliers, and these could be due to the incorrect sensor reading or the real anomalies. Yellow and green and red clusters mostly represent expected behavior. However, we also note that without the additional validation, some anomalies might not be confirmed solely. So this kind of analysis helps plant operators and data scientists prioritize their observation required further the investigation or not. So this is a critical part of any IoT-driven predictive analytics. And once the clustering analysis is complete, the role of subject matter expert or the service engineer becomes crucial. So their job is to interpret the output, not just from a statistical point of view, but through the lens of engineering judgment and their field experience. So they need to assess whether the identified cluster are within acceptable operating ranges or truly outliers that may indicate faulty operations or sensor issues. So in this context, the outliers are extreme values that lie far from the expected mean or median. Anomalies, on the other hand, may not be as far off and but can still indicate early signs. So we have to, when we talk about the outliers and anomalies, these are two different things. Okay, so outliers are extreme values that lie far from the expected mean or median, while anomalies, on the other hand, may not be as far off, but can still indicate early signs of abnormal behavior or a trend or shifting in the system. So in the IoT setting, this validation process allows us to filter out false alarms while ensuring that we catch real problems early before they escalate into critical failures. So this 3D scatter plot helps us to visualize how clustering group sensor readings based on the active power, um, air temperature, and yeah, and other operational metrics. So this is a key step in building the trustworthy predictive maintenance systems that rely on like human experts. This is very important. Human experts to confirm that the machine learning model is suggesting whatever it is suggesting. Okay. Right. The next thing is another example. In this in this step, we actually move from the clustering to targeted anomaly detection. This is another critical part of IoT analytics. One powerful method used is the COF, connectivity based outlier factor. So these algorithms fall under the family of outlier detection, outlier detection family. And the goal of outlier detection models, the goal is to identify the data points that deviate significantly from the rest, so possibly indicating the fault, degradation, or sensor issues. So here is how it works. So COF algorithm score COF score COF scores each data point and a value greater than 1.0 typically. And this shows indicates an anomaly observations. Okay, so however the algorithm alone cannot make the final call. So that's where the domain experts or SME comes in. They examine these suggested flagged. So basically what we have is we have flagged, this method raises flags. Okay, it raises flags, and the domain expert will examine in the context of machine behavior and uh, physical feasibilities, for example. So once anomalies are confirmed, and then it confirms. Okay, so it verifies or it confirms. Confirms. So uh, so so once the anomalies are confirmed, future observations can be benchmarked against these, and then they confirm. After the confirmation, the future observations can be benchmarked benchmarked against these flagged patterns. Hello. So this helps detect whether the turbine is running within its normal envelope, or if there is a need to make some corrective action. So in summary, CUF adds intelligence to your monitoring system. Okay, so the COF adds intelligence sorry. Okay, so CUF adds intelligence to our monitoring system. And the the subject matter expert add the context, and subject matter expert adds context. Together they make the anomaly detection in IoT possible. So overall, this gives us the reliable and actionable IIoT analytics. Right. Okay. So now let's we look at the practical output of COF based anomaly detection process. What we see here is a turbine dataset processed through the COF algorithm, and in this table, each row is basically at a certain time step. Each row we see a time step. This is the time. Okay, each row is at a certain time step, and multiple sensor columns. We have multiple sensor columns. These are multiple sensor columns. Okay, for example, some maybe pressure, temperature, or vibration. And most importantly, the outlier score. This one, this is the outlier score. So the outlier score column highlights the different or disconnected uh, how different or disconnected a point is from its neighbor. So if its score is greater than 1.0, so this indicates the potential anomalies. Okay, right. So the higher the score, the more reading deviates from the normal operating patterns. So this step is critical in also in the IoT pipeline, and the system flags the unusual data points in the real time, while the domain expert then visually validated if they are actually false or not. Sometimes there are sensor glitches or some other problems are there. So in short, this is where the raw sensor telemetry becomes actionable insights, a core pillar. This is a very core pillar of the prescriptive maintenance in the smart industrial systems. Okay, so this is um, overall, this is very core core pillar of prescriptive maintenance in smart, where we have implemented the IoT industrial system. Okay. Right. So this is the last slide on our predictive analytics. So in this final step, we shift from anomaly detection to the prediction. Now we know that we have we now use we can use the neural network for as a powerful supervised learning algorithm to train the detected anomalies. And once we have the confirmed anomalies, anomaly points using COF or other techniques. So let me like having confirmed anomalies. For example, after using COF method or other methods or others. Okay. Now we can go and we can label and we can train a neural network model, and from here after training onwards, any new real-time data coming from Turbine is passed through the trained model and the system. So automatically it detects whether the equipment is operating normal or not. So it is like a, so if there is any risk of failure or performance degradation, this will be detected. So basically what we have done is we have now, we usually call it like we have closed the loop with IIoT. Okay, so we have the plant, we have the data, then we have the analytics methods, and finally it is again through the IIoT we are able to continuously monitor everything. Okay, so this kind of intelligence is basically once you use your IIoT to achieve this, and this is the value you add to industry. Okay, right. So I will end this lecture here, and the next topic about the digital twin we will cover in the next recording. Thank you very much.